Assalamualaikum warahmatullahi wabarakatuh, my friends. I am Hedi Rawan. Welcome to Introduction to Artificial Intelligence. We are still in reasoning algorithms, and today we will learn about fuzzy logic. The slides are prepared by Mr. Anditya. All right, let's get started. Fuzzy logic is one of the most popular reasoning algorithms. Let's find out why we want to use it and how it works. Human experts usually rely on common sense, meaning they don't always require precise information, input and output. And humans tend to be adaptive. This is in contrast with computers and algorithms that require specific input, output, and precise numbers. So the question, if we have problems that is quite fuzzy, is how can we represent expert knowledge that uses vague and ambiguous terms in the computer? And the answer is first, computers need to learn to accept noisy, imprecise input. And second, based on that input, computers need to be able to decide not just strict true or false, but also graded truth. So meaning truth values between true and false, because not everything is either or, true, false, black, white, on, off, etc. So how to make computers understand there are things in between these true and false. Examples of the kinds of things in between are like temperature. You have like very cold, quite cold, very hot, and height. You have quite short, quite tall, very tall. Speed, very slow, normal, fast. Distance, near, a bit far, very far. Beauty, beautiful, really beautiful, gorgeous, and so on. You get the idea. And in fuzzy logic, this is reasoning using linguistic terms. So the reasoning itself is using linguistic terms. So instead of saying in programming way, if temperature is less than maybe 2.52 degrees, in fuzzy logic, we want to say if the weather is cold, okay, this is cold, not a number, then wear warm clothing. But then using a sentence like this makes us ask a question, okay? How do a computer knows what is cold? And what happens if the temperature is somewhere between cold and normal or hot? What will the computer decide? To be clear, fuzzy logic algorithm itself is not fuzzy. Yeah, fuzzy logic is a very clear algorithm, but the fuzzy logic algorithm describes fuzziness. So fuzzy logic itself is the theory of fuzzy sets or sets that calibrate vagueness. So a bit of warning, this is not uncertainty. Uncertainty is about probability. So probability is like when you roll a dice, you can get a 6. So the probability is either you get a 6 or not get a 6. You cannot get like 5.5 in dice, right? But fuzzy is for grade of values. You can say 39 degrees Celsius is hot, but 38.5 degrees Celsius is also a valid temperature and is you can say it's quite hot. Yeah. So I hope that clears up the distinction between probability and fuzzy. So fuzzy logic belongs to a computing field called soft computing. And fuzzy logic supports other fields, including probabilistic reasoning, neural networks, chaos theory, and evolutionary computation. Let's take a look at what problems we can solve using fuzzy logic. A university wants to provide some scholarships to their outstanding students. And several students have applied to the scholarship program. Let's assume we don't use fuzzy logic. What criteria can we use to accept or reject the scholarship applicants? Let's say based on their GPA or IPK, okay? If GPA is 3 or greater, then we accept the scholarship application. And as you can see in the chart on the right here, this represents the GPA score, and this represents the output of the decision. So up to below 3.0, the result is not accepted, and 3.0 or above, the result is accepted. So this is simple, right? But what if we want to prioritize students who have low family income? So we can add a rule like this. So not only GPA needs to be 3 or higher, but the income must be less than 10, maybe 10 million rupiah. Okay. So is it good enough for now? But then we find a case where a student's family is really poor, but the GPA is very near to 3. And actually, because student A here is, it's quite rich, then we actually want to accept student B here, because student B needs the scholarship more. And now this rule doesn't work, okay? So we can add a rule, and if GPA is 3 or above and income is less than 10, or if income is below 5, then we can accept if the GPA minimum is 2.5. Okay. Now you can see that the rules are already getting more complex here, yeah? And now what if we only have 5 scholarship slots? But after using that logic, now we have 6 qualified applicants. So we need to keep 5 people, and then we need to drop 1 people. Who to keep and who to drop? And maybe we can try to change the if-else criteria into scoring system like this, okay? Based on GPA, and we divide, and then income, use a formula. And now the rule becomes a combination of if and else, and also the scoring formula here. But okay, that kind of works, but what happens if we have more rules? Okay, we can maybe modify the rules, but can you see where we are going with this? The rules are getting more and more complex, and it's getting harder to understand the logic and formula, and it's more difficult to change too, okay? And it's easier to make mistakes here because it's easy to get confused. The conclusion is when we use the normal rules, programmatic rules, for reasoning problems like this, we get complicated function. It's not easy to modify. It's not intuitive. Many hard-coded parameters, and it's not easy to understand. Okay? So that's where fuzzy logic comes to save your problems. Yay! Okay. So the first concepts that you need to understand are fuzzy value and fuzzy set. The normal facts that we learned before in propositional logic and first order logic, they are crisp facts, okay? So like the weather is hot or not hot, the weather is cold or not cold, Andy is tall, Andy is short. Okay. But fuzzy facts, they have a grading. Okay, so a temperature can be hot or cold or something in between. Okay, someone's height can be somewhere between very tall and very short. Okay, and this is different than probability. Yeah, probability is for might be or a chance. So there's a chance that weather is cold today, but it might not be cold. So we are talking here about the probability of cold weather, not about the intensity of coldness. Now we have the concept of crisp value and fuzzy value. Okay. As you can see here, a fuzzy value consists of a crisp value here. This one is the crisp value. But there's also a gray area that transitions the value between 0 to 1. Okay, from 0 to 1, from 0 to 1, this is from 0 to 1. This is if we see from above, yeah. And this is if we see from the side, this is from 0 to 1. So this gray area are the fuzziness. So this is the input and the output can be from 0 to 1. And there is a gray area here, okay, the fuzziness area. And if we look at crisp sets here, in height we have short and average and tall. And you notice that these ranges are crisp. So there is no mistaking. For example, if the height is 169 centimeters, this is short, okay? It's definitely not average. It's definitely not tall. But if we use a fuzzy sets concept, things can be mixed in the grade of truth, okay? For example, if the height is 169 centimeters, this is here, right? And if you see here, there is a short range here and also an average range here. So that means 169 is maybe about 0.1 short or maybe 10% of shortness. And based on average, it's maybe about 0.4 average or maybe 40% of averageness. So using fuzzy set concept, 169 centimeters is both short and also average. Okay, and there is also a membership degree in both the short one and the average one. Okay, it's still possible. For example, if you 190 centimeters, this will be like 100% tall, and it's 0% average and 0% short. But as you can see here, most of the height values become multiple membership with varying degrees of each of short, average, and tall. To review, probability is about likelihood or a chance or might be, and fuzzy logic deals with degree of membership in a set. Okay, after the concept of fuzzy value, there is a concept of linguistic variable. A linguistic variable has values that are words or sentences in natural or artificial language, and these are not numbers. Yeah. For example, a linguistic value is like young, not young, very young. This is age. Yeah. If we have a linguistic variable of age, it's not 20, 21, 22, but the values are young, not young, very young, quite young, old, not very young, very old, and so on. Okay, so these are linguistic terms. Okay. So fuzzy logic treats truth, which is normally it's true or false, as a linguistic variable, meaning that truth values are ranging from like very false to somewhat true and then to very true. So this is the basis for approximate reasoning. Okay, to solve problems that are closer to human reasoning than traditional true-false logic. The next concept we need to learn is membership function. Membership function is a formula that maps a crisp value, we can say u, into a fuzzy z a, and the value is an interval from 0 to 1, inclusive. Yeah. So continuing our previous example, let's say the height is 169 centimeters, and that means the degree of membership for short is 0.1, and the degree of membership in average is 0.4, and the degree of membership in tall is 0.0. Now we need three membership functions, yeah, for u for the short one, and then we also need the membership function u for the average one, and we also need the membership function u for the tall one. Okay, so the input for all of this function is the height. So for example, we can input 169, this one is 169, the input here is 169 as well, and the output, the function result, is a number between 0 to 1, so indicating the membership in short, average, and tall. So the example here, the u for short will be 0.1, and u for average, this will be 0.4, and this one will be 0.0. Okay. So this is another example. We have input the crisp value is a temperature in Celsius. Okay. And we have a fuzzy temperature with three linguistics cold, warm, and hot. This means how many membership functions we need for temperature. Okay, correct, 3. So we need a membership function for cold and warm and also hot. So these functions, when given an input of 5, cold function will return 1, the warm function will return 0.1, and hot will return 0. Okay, this is how membership functions work. Membership function is usually described as a linear function, okay? Although it's also possible to use sigmoid and Bell function. So the example on the right here is a membership function that is decreasing, okay? From 1, when input is A, it gives 1 as the output, to decreasing to 0 when the input is B. So you usually use this shape for linguistic that is the beginning or the lower edge. Yeah. For example, for short, okay, you can use something like that. Okay. And the example on the left is membership function that is increasing from 0 when input is A, and then increasing to 1 when the input is B. Okay. So you usually use this shape for linguistic that is the ending or higher edge. Okay, for example, for tall, you can use this one. And we can combine increasing and decreasing function, so the shape looks triangular or trapezoidal. Yeah. So this one is usually used for linguistic in the middle. Okay, but yeah, we can use this for beginning or ending. So in the middle, for example, average, it can look like this. Average can look like this. Yeah, for average height, the linguistic, the membership function for average can look like this or like this. Other than linear, sigmoid function can be used, and then it will give a smooth curve. Okay, and other nonlinear functions can be used like beta function and Gaussian function. We have learned the fundamental concepts that are fuzzy sets, fuzzy values, and membership functions. So let's see how fuzzy logic works. In a fuzzy system, there are three processes: fuzzification, inference, and defuzzification. In fuzzification, the inputs are crisp values, okay, and we also have membership functions for each of the linguistic variable. The fuzzification process transforms the crisp input into fuzzy input values based on the corresponding membership function. Okay. And then in step 2 is inference. We determine the fuzzy output using the predefined fuzzy rules. And then in step 3, defuzzification, we transform back the output fuzzy value into a crisp value, and we will also have membership output membership function here. Okay. So we need 5 components for building a fuzzy system. First is we need to know the number of input and also output linguistics, and then we need to know the input membership functions, and then we need to design the fuzzy rules, and then we need to determine the defuzzification method. There is Mamdani and there is Sugeno, and then we need to know the output membership function. Okay, all right. Ideally, these are provided by the expert, but in the exam, you will be given a problem, and sometimes some of these components will be given by the exam, but if not, then you will need to design it yourself. Let's take a look at an example, the scholarship selection. First, we must design the inputs and outputs. So all inputs must be designed as linguistic variables, okay, and also the outputs. So in the scholarship scenario, we have 2 input linguistic variables. The first is the GPA, and then with linguistics high, average, and low. And the second is income, with the linguistics are upper, middle, and bottom. Okay, and then the output linguistic is score, and we design also 3 linguistics here: accepted, considered, and rejected. In step 2, we must design each membership function for each linguistic as a formula. Okay, so how do we design this? So let's start with the membership function for GPA, and we start with the first linguistic, and that is height. Okay, so we know that the range of GPA is from 0 to 4, right? Inclusive. And then we must decide what is the range for height to be able to design the shape of the membership function. So let's say the GPA of more than 3.25 is definitely high. Okay, but below that, below 3.25, below 3.25 is quite high, but not below 2.5. So below 2.5, that will be not high. Okay, so there is a range of from 2.5 to 3.25, and that is the fuzzy area. Okay, between high, between not high and high. Okay, and then we will use linear function here. So this is what we have. Okay, so as you can see here, from 0 until the GPA is 2.5, it is definitely not high. So the result of the function mu height is 0. Okay, and then beginning from GPA 2.5 until 3.25, the result is increasing. Okay, the result of the membership function mu height is increasing. And then from 3.25 until 4, the result is 1. So meaning is definitely high. So in the mathematical formula here, you can see that this line here corresponds to the formula if x is less than or equal to 2.5, and then the result is 0. Okay, this one. And this increasing line corresponds to the formula here. Okay, so from 2.5 to 3.25 is here. And this horizontal line here corresponds to this one, because when x or input is larger than 3.25, then the result is 1. Okay. So this formula here, mu height x, is the input membership function for GPA height. Are we done? Not yet. Remember, we have to do this for all membership functions. So for GPA, not only height, but we also still have average and also low. So these need membership functions too. And there is also income input, upper, middle, and bottom. So we need to create membership functions for them too. Okay, so this is the membership function for GPA low. And this is the membership function for GPA average. As you can see, the shape here is trapezoidal. Yeah. So in the mathematical formula, you can see that this line here, 0, the output is 0, from 0 to 1, the input 0 to 1, corresponds to the formula here. Okay. Note that this is both for the starting and also the ending here. So this one is starting. If GPA is from 0 to 1, and if GPA is from 3.5 to 4. Okay, so the output is 0. So definitely not average. Yeah. And if GPA is either around from 1 to okay, so yeah, and this increasing line is from 1 to 2.2. This corresponds to this formula here. And then we also have from 2.2 to 2.8 here. And this will be here. So the result is always 1. And then from 2.8 decreasing to 3.5. And this will be this one. Okay. And if we combine all of the membership functions for GPA, low, average, and high, it will look like this. The red line is for low. The blue line here is for average, and the green line from here is the high one. Okay, that's done for the GPA. Okay, so but we need to do the same membership functions, similar membership functions for income, which is lower, middle, and upper. Okay, so let's see that these are the membership functions for income input linguistic variable, and we have the bottom linguistic, the bottom membership function, the purple line, and then the middle linguistic, the brown line, and also upper, the blue line. And then in step 3, we must design the fuzzy rules. This means we define rules that will determine the accepted or considered or rejected score based on the GPA and income inputs. And the format is like this in pseudocode. But maybe it's easier to show this in a table. Let's see how it looks like. So this is the fuzzy rules as a table. Okay. And usually you will need to design this if it's not in the exam, but sometimes the exam will tell you the rules. So how do we read this? Let's see. This one means if the student's GPA is high and the parent income is upper, then the output score is considered. Now, how about the second rule? If the GPA, the student GPA is high, and then the parent's income is middle, and then the output score is accepted. Okay, so that's how we read it. And you need to have these rules for all possible combination of input linguistics. So if you have 3 GPA and then you have 3 linguistic for income, that means 3 multiplied by 3, then you need to have 9 combinations. Okay. And then the step 4 is you need to choose the defuzzification method. Okay. So at this step, we will have a fuzzy output value, and we need to transform the fuzzy output value back into crisp value. And the common methods that we will learn here are first center of gravity, or we call it Mamdani style, and then second one is constant defuzzification or Takagi Sugeno style. Okay, and let's check out Mamdani. Okay, using Mamdani, we need to define output membership functions. Okay. In this case, we have the rejected line, the pink line, for output values lower than 40 or 60. Yeah. And then the considered line is the gray line here, is for output values between 40 to 80. And then the accepted line, the black one here, is for output values between 60 to 100. And then when we do this, we need to chop off the membership parts of the membership from the rule inference output. Okay, so we will discuss how exactly to do this later with concrete example. Yeah. With Takagi Sugeno style, we don't need to make output membership function, but we simply need to define a constant number value for each output linguistic. For example, here the rejected is 50, for considered is 70, and accepted is 100. And as you can imagine, Takagi Sugeno defuzzification method is simpler to understand and implement. So if later you are confused with Mamdani, I suggest you use this one. Your fuzzy logic implementation will still be correct. So let's use a real example with real numbers, yeah. The scholarship selection. For this example, we will compare two students, student A and student B. Student A has a GPA of 3.01 with a parental income of 14 million rupiah, and student B has a GPA of 2.90 with a parental income of 5.5 million rupiah. Okay, our job is to find out the output score for each of the students using fuzzy logic. So if we only accept one student, which one will get accepted? First, we need to design the input membership functions. Yeah, this is as in previous slides. Now, after we have designed the input membership functions, the GPA number for each of the student, we evaluate the formula for the mu high, mu average, and mu low membership function. For example, this one is membership function for height. Okay, this one is membership function for height for student A. Okay, this one, and then and this one is a membership function, membership value for height for student B, and this one is for average student A and average for student B, and then the low membership function and value for student A, and this is the low one for student B. Okay. Now we have the fuzzy values here for each student, but only for the GPA input linguistic variable. Are we finished? Yeah, not yet, yeah, because we have another input linguistic variable, and that is parent income. Okay, so let's calculate the fuzzy values for parent income. Okay, so the parental income numbers for each student, we calculate the formula. This is the membership function for parental income. This one is for upper student A, upper for student B, middle for student A, and middle for student B, bottom for student A, and bottom for student B. All right, we have all of the input fuzzy values here. What next? Yep, we need to define the rules to map or perform inference from the input fuzzy values into the output fuzzy values. So this is the inference step. In this step, we need to use the clipping technique. Okay, we will look for each relevant combination from the rule table, and we put the input fuzzy values there. And then the output value, the output score will be the minimum from the input values. Let's see an example. Yeah. So for student A, okay, the GPA hike membership is 0.68, yeah. And then the income for the upper membership is 0.5. And from the rule table, we know that if the GPA is high and the income is upper, then the score will be considered. Okay. But then, how do we fill the numbers here? We fill the numbers here based on what is the minimum value or the lower number. Okay, so because the minimum value is 0.5, then we put 0.5. Okay, then you use the same method. Okay, this one, the minimum is 0.25, so this counts 0.25. Okay, so before we go to the next slide, please notice, hold in your mind that for student A, okay, the score for accepted here has three fuzzy values, yeah. This one accepted 0.85, this one accepted 0, and then this one accepted 0. We will use that in the next slide. Okay. After doing that, we need to get the fuzzy values for each output linguistic. Okay. So we need to make the accepted value into a single number, considered into a single number, and rejected into a single number. The way we do it is by getting the maximum value for each of the fuzzy output linguistic. So as you recall from previous slide, for accepted, for student A and accepted, the values are 0.25, 0, and 0. That means the maximum value from these three numbers are 0.25. Okay, and then we do the same for considered and also rejected for student A and also for student B. Okay. Okay, and then the last step is defuzzification. Let's try Mamdani first. Okay. Remember, when we're using Mamdani, we have to design the output membership functions like this. Okay, but this is already clipped, yeah. So when applying Mamdani, we clip the results from each of the membership function, the output membership function, yeah. And so for accepted output member function here for student A, the results are clipped at 0.25. As you can see, this is clipped, yeah. So it's not full. Okay, it's clipped here. And then for considered, the output is clipped at 0.5. And then for rejected, the output is clipped at 0. Okay, so meaning that you don't see anything here, right? And then you do the same for student. Okay, we will review this in more detail in the next slide. And this is the equation for Mamdani defuzzification. Okay, so to calculate the crisp output, and that is the score, yeah, we can generate random numbers, n random numbers. For example, here 10 random numbers, and then we clip the output values of the formula. Okay, so let's see what we mean by clipping the numbers. Okay, so first we calculate the membership of each of the random generated numbers. So we have 5, 15, and so on. Okay, and then we evaluate the output membership function for 5, 15, and so on. So we have three output membership functions, right? When we evaluate the output membership function for rejected, and then the input is 5, we get 1, and so on. And this is what the considered, and this is for the function of accepted. Okay, and the table is what we get here. But then we clip these numbers based on the fuzzy output values for each student. So as you can see, the accepted one for a student A is 0.25. So even though this should be the output membership function, but then it gets clipped here, okay, 0.25. So how we do this using the table is that although these actually have bigger numbers, okay, but then we clip to 0.25. And we do the same for consider. We clip anything greater than 0.5 to 0.5. And then for rejected, well, because it's clipped at 0, that means that everything in rejected is 0. And then we output values for each row here at the maximum value. Okay, so we have the output values of each row here at the maximum value from accepted, considered, and rejected. Okay, so let's take a look for zi equals to 45, because between rejected 0 and considered 0.25 and accepted 0, the maximum is 0.25, and that means the output for zi 45, the output is 0.25. And then we do this for all of the zi values. And last, we use the Mamdani equation here and use all of the numbers here. So we multiply 5 to 0, that equals 0 here. Multiply 15 to 0, that equals 0 here, and so on. We multiply 45, multiply with 0.25, we get 11.25 here. Okay, and so on. And then the lower part here, okay, the lower part here is the sum of all the mu b numbers. Okay, and so this becomes 135 divided by 2 for student A. And finally, the score, the output score crisp value for student A is 67.5. And that's it. That's the final score. So let's do the same for student B. Okay, we do the same. And using the same method, student B gets a score of 78.21. And now we have the output score crisp values. Now it's easy to know who has priority to get the scholarship, right? It is student B, because he or she has 78.21, while student A gets 67.5. So if you have many students and many scholarship slots, then you do the same thing for each of the students, and you sort based on the biggest output scores, and the students with the top scores will get the scholarship, and the rest will be rejected. So that's it. If our defuzzification method is using Mamdani. Okay, let's see what if we are using Sugeno instead. Using Sugeno defuzzification is simpler. Yeah. So these are the fuzzy output values for student A, and these are the fuzzy output values for student B. With Sugeno defuzzification, we need to set values for each output linguistic. Okay, so here we set score 50 will be rejected, score 70 will be considered, and score 100 is accepted. Okay, so this is the Sugeno formula, and we will show you how to use it. Okay, so what you do here is you multiply the student's fuzzy output values to the linguistic membership value. So the fuzzy output value for student A accepted is 0.25, so you multiply by the accepted output membership value, and that is 100. And then you multiply, this one is for considered, yeah, 0.5 times 70, and this one is for rejected, 0 times 50. And then the bottom part here, you sum, you add all of the student A's fuzzy output values. Okay, and then you get that the student A score will be 80. And with the same method, you get the student B score is 93.67. So who gets priority for scholarship? Yes, that's right, student B again. As you can see, the output scores are different with Sugeno than with the Mamdani before. But in this case, the decision is still the same, that student B gets the priority. However, if the output membership design is very different, it's possible that Sugeno will output a different result than Mamdani. They output a different decision, which is okay as long as you implement the algorithm correctly. All right, my friends, and that is our discussion about fuzzy logic algorithm. I hope this has been pretty clear for you. After this, it will be time for you to code a program and implement the fuzzy logic algorithm using Python programming language. See you again in the next topic. I am Hendy Irawan. Wassalamualaikum warahmatullahi wabarakatuh.